Tooling incorporates thousands of different cutting tools and tool holders for discrete parts manufacturing. Principal categories within cutting tools include single-point cutting tools, such as lathe tools, multi-point cutting tools, such as milling cutters, drills, reamers, and taps. Cutting tools are either standard tools, which are purchased as catalog items, or special tools, which are designed and built for a special machining job, often to suit a particular workpiece. The main objective in the selection and application of cutting tools is to safely machine a workpiece in the shortest possible time while meeting the part's quality requirements. Furthermore, the specified tooling should be the least costly and least complex tooling available to satisfactorily fulfill the qualitative and quantitative workpiece demands. It is estimated that nearly 50% of all cutting tools are used incorrectly. Additionally, the number one error when formulating tooling selections is calculating monetary savings based on lowest cost per tool rather than on maximized productivity and extended tool life. To effectively select tools for machining a part, a machinist must have specific information about the workpiece, such as the starting and finished shape, the hardness, the tensile strength, and abrasiveness of the material. These factors all influence the interaction between the tool and the work. The machinist also needs to know whether the workpiece material breaks into short chips easily or whether it tends to flow into long, hard-to-break stringy chips. Also important is the part's work-holding setup, which properly orientates and holds the workpiece, and the power and speed capacity of the machine tool. Changes in the workpiece material, part tolerances, geometries, and quantities required often demand corresponding changes in the tool materials and/or tool geometries selected. For the wide variety of machining applications, there is a corresponding necessity for different cutting tool materials. The ideal cutting tool material should be harder than the workpiece it is cutting, be able to retain its hardness and stability at high temperatures, resist wear and thermal shock, be impact resistant to withstand the mechanical shocks of milling, and also be chemically inert to the work material and the cutting fluid. No single cutting tool material incorporates all these qualities. Instead, trade-offs occur among the various tool materials. For example, materials with excellent chemical and thermal stability, such as ceramics, tend to be brittle, with limited resistance to mechanical and thermal shock. These variable properties take place both within a material class, such as different grades of carbide, as well as when comparing different classes of tool materials, such as high-speed steel and carbide, or carbide and ceramics. All cutting tools have a working life, and then they dull, fail, or fracture. For this reason, they are called perishable tools. The cutting tool life cycle may be a single use or involve indexing to multiple edges, as with an insert, or multiple resharpening, such as with drills, end mills, and taps. It is a safety hazard to run any cutting tool until it breaks. This creates scrap, impacts tool and part costs, and reduces productivity. Aside from breakage, cutting tools wear in many different ways. Edge wear and flank wear are both a normal and slow type of tool wear. In carbide turning of steel, it often occurs after 15 to 30 minutes of cutting. If the work material is highly abrasive, such as with certain cast irons, this type of wear will accelerate. To correct this problem, select another more abrasion-resistant tool grade. Cratering, or top wear, behind the cutting edge occurs commonly in machining long chipping steels, from abrasion and diffusion wear. If the crater grows large enough and contacts the cutting edge, the tool fails immediately. To combat cratering, use hard grades of carbide with tantalum carbide or titanium carbide and hard coatings such as aluminum oxide or other materials such as cermets or ceramics. Chipping on a tool edge is an unpredictable form of tool failure. It is sometimes started when a high point on an edge breaks away. A stronger carbide grade, different edge preparation, or lead angle change may eliminate chipping. A built-up edge is a deposit of workpiece material adhering to the rake face of the insert. Chips weld themselves to a cutting edge. Sometime later, the deposit breaks off and pulls small pieces of carbide out of the edge. This occurs at or just behind the edge. Ductile materials such as low-carbon steel, soft aluminum, and copper cause this damage. Higher rake angles, faster cutting speed, and higher pressure cutting fluid all help eliminate built-up edge. Deformation takes place at very high temperatures, 1800 to 2000 degrees Fahrenheit. These temperatures cause the insert binder material to soften, depressing the top surface and mushrooming the sides out into the clearance angle, where it is abraded away. Deformation is difficult to detect without the use of a microscope. A deformation-resistant grade and/or high hot hardness coating is required, or else reduce the operation speed to reduce the heat. Thermal cracking occurs when inserts go through a rapid heat-cool cycle, such as in either interrupted cutting or when the coolant is improperly applied, suddenly cooling a hot insert. A notch at the depth of cut line may occur in machining high-temperature alloys or with any very hard outer layer, such as in a casting or forging. This is caused by the pullout of small particles of tool material at the flank, face, and cutting edge by the pressure welding of work material to the tool material. An edge preparation on the insert and an increased lead angle may decrease notching. These are only some of the natural causes of tool wear. Maximum tool life can be achieved through selecting the proper insert or tool material or altering the cutting conditions.